My name is Roman. I'm working in Bitfury. Especially, I'm working on Exonum project. Exonum is a framework for building private blockchains, and especially I'm developing a blockchain application based on Exonum. I have a question for our audience. How many did you have experience with blockchain or any related technologies? Please raise your hands. Okay, nice. It's cool. So I'm going to address the problem with my presentation today. Okay, we have IT system, we have blockchain, but how are we going to provide the final user the proof that the data is actually stored in the blockchain, that the data is have the same state as it was before when the transaction was recorded. And I'm going to explain how we did and solved this problem with our solution, with Exonum. A couple words about the company. So Bitfury, it's a global blockchain company. We started as a hardware company. We started with the mining. Then we opened the software branch. Now we have 3 products. The first is Exonum. It's a framework for building private blockchains. The second is a pitch. It's actually a Lightning wallet that allow to make Bitcoin transaction, make it faster and cheaper. And the third is Crystal. This is a tool for making investigation in Bitcoin. Let's move on to Exonum. The first part, I will explain a little bit what Exonum is and what is like main feature we have. The second part will be I will explain what is the proof is, a little bit theory part, and how we implement it in code in our solution. And the third part will be demo. So the Exonum. It's open source framework for private blockchains. What's private blockchains? So it's usually blockchain that can be used between some organizations. Usually some organizations have like the shared business process and they want to share the data also. And this organization usually don't trust each other, but they need to exchange the data. So in these cases, private blockchain can be useful. Exonum, so it's already open source for about 1.5 years. About 30 developers working on this project, and mostly it's Rust developers. And so it's a pure library and business business logic. It's up on the developers who trying to build something on top of Exonum. As a consensus, we're using BFT consensus. This allows we build it ourselves. It allows to show the speed of transaction processing up 5,000, and the latency is about 0.5 seconds. It's mostly for the network delays, plus it's for block issuing, and we're using standard algorithms that everyone using in the industry. We also develop the technology anchoring when it's useful for example, if we have 4 nodes and we have BFT consensus with 3 nodes, and it can be happen that 3 nodes can agree to cheat the first nodes. And so what the first node can be doing in this case? So for this case, we introduce the anchoring technology. What it actually do? So we get the hash of the block, and for example, each 1,000th of the blocks, we are publishing this information to public blockchain network. Especially, we are publishing the data to Bitcoin as the most secure solution nowadays. Also, we have a light client. So actually, it's a JavaScript library that allows to make easy integration for web applications. It has all built-in functionality for forming transaction, for make data audition, and also to make anchoring verification. we have the raw model of our nodes. We have actually 3 types of the nodes. The first node is validator. It's the node who stores the whole copy of the data, and also it's this node is involved in the consensus. Also, we have auditor node. So it's not quite the same as validator, but it's not involved in the consensus. And the client, light client. So usually it's integration part. It's do not store any information from main nodes, but it's have all the functionality to get the proofs and to calculate all the proof on their sides. So usually on this side we are using our JavaScript library. Okay, let's move on to cryptographic proofs. Firstly, I will start a little with theory, and then it will be more closer to the code and to our solution. The first, our Exonum storage based on the RocksDB, so it's an embedded key-value storage. As a collection, we have like the usual persistent collections. It's a list, it's a map, it's a set. And also on top of it, we have some merkelized collections. We call it proof map index and proof list index. About this collection, I will talk a little bit later. And also in the storage, we store our transaction log, what actually is blockchain is. RocksDB, so it's, as I said earlier, it's a key value storage. The key and the values are stored as byte arrays. And the keys are ordered based on the key value score. As I said earlier, we had merkelized collections. It's proof map index and proof list index. And these actually collections based on Merkle 3 data collections. So what we are using this for, the first for the audition to calculate the path of the data from the database, and the second for consensus for our synchronization of the data. This is whole picture how the data is storing in our database. So here we can see will be our tables that presented as Merkle trees. For example, this one will be a table with name timestamping. This will be some another tables. Let's call it users. And then, as we have the Merkle hash that describes all the information of the table, you can collect the whole the one common table or common tree that from this tree we can calculate the Merkle tree of this Merkle root of the tree. We will call it state hash, and then we will publish it in block header, and then this block hash we can also use it for anchoring to publishing it in Bitcoin network. So how the Merkle tree is looks for? Look, so basically it's a tree. In the leaf we have the data, and in the branch we have the hashes that calculated pair by pair from the trees. And on the top we will receive the Merkle root hash that allow us to describe the data. How do we encode this data in our database? So we are using as a key value storage. For the key we are using okay. So for the key we have we encode the key. So we need to encode our tree with some indexes. So how do we encode it? So the key consists with height and index. The height is the height of the tree, and the index is the position, like if we call it horizontal key in the tree. This is some kind of example how some values will be stored in the table. And let's move to the proofs. So it's a simple example. We have a very small tree, and we want, let's pretend that it's case and user want to know what is the path, what is the proof path for this value and for this value. So the actual path will be like, for this value will be like here, and for this value will be like here. We will encode it as a JSON file, and this JSON file we can send to the client, and the client on his side can calculate by himself the state and compare it with the state that written in blockchain. For the proof map index, we use a little bit different data structure. It's Merkle Patricia tree. It's based on the radix tree, and so let's just remember how radix tree works. We have some index, and based on similarity index, we are building the tree. For example, if we want to search the value that encoded with index Romain, we will follow this path, and on this path we will have some similarities, and this we can find the switches. For Merkle, whereas for Merkle Patricia tree, for index we are using hash, and the mechanism will be kind of the same, but for the index we will be using hashes. Again, let's return to the 4 our pictures. We have our database, and the user now want to request. So we have working system, and the user want to through the web client want to request the proof. He has some record, and he want to get the whole proof how his data records stored in database. This is how it will be look how. So, for example, I'm asking for the data with ID Bob, and the full proof path will be like here. So we will follow the path in timestamps table, then we will follow the path in our common state hash table, and also we want to receive some information from the blockchain, related to the blockchain. Now it's part for the demo, but firstly I want to quickly go through the code of our application. The demo will be based on the simple application. It's we call it timestamping. So basically how it's works, we have the file, calculate the hash of the file, and we put it in, we write it in the blockchain. Why we need it for? We need to make a proof that this file has the particular state in the particular time. Firstly, we are forming our transaction. It will be JSON, and we are sending it to our node. Then the node has the REST API handler, and here we will. So what we will do? So we will calculate the hash of our input transaction. Then we send this information to peer-to-peer network, and we will respond with the hash of this transaction. Here we are describing our transaction. And this is our business logic, what we will do with our transaction. First, we will verify our transaction, and the second, we will do some execution code. Here we will call our database, checking that this is a new record, and then we are writing this record to database. And this is how we will describe our database. Here we can see our proof map index, and we call our table with timestamps. And this is auxiliary function to write our data to database. Okay, let's move on to demo. Okay, first I need to stop presentation. Okay, some technical problems. Okay, let's work like this. Ooh. So first I start the node. No, it's not going to work in this way. Now it's working. Okay. So I have started the node. It's started to work. Then I will start my web application. Then I will go to my web application. The interface is quite simple. So what I can do from this web application, I can upload my file, write some metadata, and send this information to blockchain so we can follow the transactions and check check how it was stored in blockchain. We can see that it's stored in this particular block. And let's, I need to upload a little bit more files. The file 2. File 3. Okay, now we have this file, and I'm going to search for this file in my interface. And when I call this search, actually I'm call the API endpoint, and the API endpoint provide this type of information. So what we have here, we have our information about who was called for this transaction. We would then we will have the information about our state hash table, and we can see here the proof path how we can find this information. This is information. It's information about our table. So we are storing our table in our state hash table, state hash tree, and this is a proof how we will search this table. And then we have our timestamp proof. This is the value that we uploaded, and this is a proof path how it was stored in the tree. Let's okay, I can see. So what's happening on the front end side? So when we call the search button, we call this part of code. So we can see we call this endpoint that I showed just previously. First, we are verifying the block, so we are getting information with pre-commits and checking that it was okay and it was signed clearly. Then we are looking for our table in our state hash table, and we want to be sure that we are tracking this table. And then we are looking for our record actually in timestamp table, and checking our tree path on the client side. If everything okay, we will return our data. How it will look like on the Exonum on the backend side? We are getting this is our database. So we are firstly requesting the information from the database about our last block. Then we are requesting information about our blocks and pre-commits, and then we are requesting our proofs for this table. And then we are returning on this information for our client. Okay, so let's return to presentation. So as a conclusion, I can say, so the merkelized collections can provide our mechanism to build like the data that the client can be checked on his side. And also I showed how we built this approach in our solution, especially with Light Client and Exonum. Thank you for attention. I'm ready to answering for your question.
You mentioned the BFT protocol. What do you use? Is it something that you can pick any, or do you have one implementation from you?
Thank you for your question. Especially we are using PBFT algorithm. It's implemented by ourselves, so it's not based on some open source library. But as the whole Exonum open source, you can go to GitHub and check our implementation.
Okay, thank you.
Are you planning on introducing anchoring to other large blockchains?
Introducing, excuse me.
Anchoring to other large blockchains other than Bitcoin.
Yeah, we have the plans, but by now, like all like our business requirements was fully like closed by the Bitcoin. And it was by this moment it was quite enough, and this why, and also we quite big support the Bitcoin network. This why we have. But also like this also like open source, and it's quite easier to switch to another open blockchains. Okay, thank you for your attention.